Morning friends. Today we are going to discuss about the speed of a progressive wave. Right? To derive the equation of speed of a progressive wave. Already we discussed about the some terminology for the wave, the frequency, periodic time, angular frequency, wave speed, right? And also the phase. Already we discussed and wave equation. Now, after getting the knowledge about this terminology, now what is the equation of the wave speed for the progressive wave? First, the definition of the wave speed. First, we had the definition. The distance traveled by, or the covered by, a wave in unit time is known as a wave speed. What are the here? There is a progressive wave. That means the wave is propagating in particular direction. How much distance covered by the wave in unit time? That is known as the wave speed. The definition of the wave speed is same as the speed. Same definition of the speed. The distance traveled in unit time, that is known as a speed. The same definition. The distance covered by a wave in unit time is known as a wave speed. It is denoted by V. Symbol is same as the speed of a particle. Its SI unit is meter per second. Now we require the equation of wave speed of a progressive wave. Right? Therefore, to find the speed of a progressive wave, the speed of a crest on a wave is required. The speed of a crest is required. Therefore, to find the speed of a progressive wave, the speed of particle on crest is required. For this, how we find out the speed of the particle on the crest of a wave? For this, in figure, the position of particles on crest is denoted by dark circle. As we do the diagram, so there is the position and there is the displacement taken along the y-axis. Position on x-axis. So at different time, the position of the particle taking the part in the propagation of wave is shown in the figure. O point is the origin of a wave. As the wave is originated at origin, that means the disturbance is produced at origin. So the effect of this disturbance is propagate or the traveling or the propagating along the x direction. Therefore, the different particles of the medium oscillate about their mean position. That is the situation at time t. After the delta t time, the situation is like this way. So here we denote The dark circle that represents the position of particle on a crest. At time t, here the position of a particle on the crest is this t. Here the position is x. After the delta t time, or in delta t time of interval, this position of the particle on the crest is which is here. So that is the position at x plus delta x position, and that is the time t plus delta t. T plus delta. Now the displacement of a particle on the string is changed, but the displacement of the particle on the wave does not change. Right? The displacement of the point on the wave does not change. For that purpose, the displacement of the particle on the string, that means the medium, is changed. But the displacement of particle on the point on the wave does not change. The displacement of point of the particle on the wave or on the string is changed, but the displacement of the point or the particles on wave are not changed, or does not change. Suppose the wave covered delta x displacement in delta t time, then the wave speed is equal to distance covered upon total time. What is the time taken for this displacement? Therefore, wave speed v is equal to delta x upon delta t. Here the distance covered is delta x and time taken is delta t. And phase kx minus omega t remain constant. Phase remain constant. Clear? Thus the position of the point on the wave changed by delta x distance in delta t time, but the phase is remain constant. That means the phase at time t and phase at time t plus delta t is remain same. Therefore, the displacement of a point on a wave changed by delta x in delta t time, but phase remain constant. Therefore, kx minus omega t is equal to k x plus delta x minus omega t plus delta t. Here the phase is even constant at time t. Therefore, the same phase at delta after delta t time and after the delta x displacement. Therefore, phase at time t, kx minus omega t is equal to phase at time t plus delta t. In delta t time, the displacement is delta x and time increases delta t. Therefore, we simplify like this way: kx minus omega t is equal to kx plus k delta x minus omega t minus omega delta t. Therefore, kx omega t cancel. Therefore, k delta x is equal to minus omega delta t. Minus omega delta t. Clear this thing? Okay. And also the total phase becomes the 0. Now in this case, minus omega t plus delta t, therefore the minus omega into delta t. Therefore k delta x minus omega delta t is equal to 0. Here the kx minus omega t, therefore k delta x minus omega delta t is equal to 0. Therefore, k delta x is equal to omega delta t. If time interval delta t tends to 0, then the delta x is also becomes the 0. It means as you consider time interval smaller and smaller, the displacement of a wave is also smaller and smaller. Therefore, as the delta t tends to 0, delta x is also tends to 0. Therefore, k dx is equal to omega dt. Now we know that dx upon dt is equal to speed. Therefore, dx by dt, that is known as the wave speed, is equal to omega upon k. Omega upon k. That is our first equation. But we know that angular frequency omega is equal to 2 pi f. 2 pi f and k is equal to 2 pi upon lambda. But omega is equal to 2 pi f or 2 pi upon t. And k is equal to wave vector 2 pi upon lambda. Therefore, equation 1, v is equal to 2 pi upon t upon 2 pi upon lambda. That means the lambda upon t. There is a second equation. And also we know that one upon t is equal to f. Therefore, wave speed is equal to f lambda. That is our third equation. So these are the equations of a wave speed for a progressive wave in a strip. Very easy. So how we obtain? Well, the question is that define the wave speed and obtain equation of the wave speed of progressive wave. Or in other words, for the progressive wave, obtain v is equal to omega upon k, or v is equal to lambda upon t, or v is equal to f lambda. First, the definition of a wave speed. The distance covered by a wave in unit time is known as the wave speed. It is denoted by v. Its SI unit is meter per second. How we derive the equation of the wave speed? Okay. To find the speed of a progressive wave, the speed of particle on the crest is required. For this, in figure, the position of particles on crest of a wave, for the crest, is denoted by dark circle. For that purpose, here we do the diagram, position versus displacement. So at time t, the wave is represented by this. It means the disturbance is propagating in the string medium like this way. After the delta t time, the position of the wave in a medium is like this, or the string is this. Here the dark circle represents the position of the particle on the crest. Now listen, the displacement of the point on the string is changed, but the displacement of the point on the wave does not change. Suppose the wave covers the delta x distance in delta t time. Therefore, the wave speed is distance covered upon total time. Distance covered is delta x, total time is delta t, and phase kx minus omega t remain constant. Okay. The displacement of a point on a wave changed by delta x. But the displacement of a point in delta t time is delta x. Therefore, the phase of a wave remains constant. Therefore, kx minus omega t is equal to phase at time t plus delta t. That means the k, here the position is increased by delta x. Yes, the time is increased by delta t. As we open this bracket on right hand side and we cancel the kx minus omega t, kx minus omega t. So remaining part is k delta x minus omega delta t is equal to 0. Therefore, k delta x is equal to omega delta t. If the delta t tends to 0, then delta x also becomes the 0. We apply this, therefore the small change in time, small change in position. Therefore, k delta x is k dx is equal to omega dt. Therefore, the wave speed dx by dt is equal to v is equal to omega upon k. Now we know that omega is the angular frequency of the wave is equal to 2 pi upon t over the 2 pi f, and k is the wave vector 2 pi upon lambda. It is substitute here the value of omega and k. We obtain the wave speed v is equal to lambda upon t. And also 1 upon t is the frequency of a wave. Therefore, substitute here. Therefore, wave speed of a progressive wave is v is equal to f lambda. Now just we did the equation of a speed of a wave or the speed of a progressive wave. Now next question is that obtain the equation of the speed of the transverse wave in a stretched string. If the string is tied from the both supports, that means the string is stretched. So what is the speed of a transverse wave? We have to derive the equation. Now, this equation is derived on the basis of the dimensional analysis by considering the dimensional formula of the factor on which the speed of a wave is depends. Right? Already we discussed in chapter 2 the uses of the dimensional formula or the dimensional analysis to obtain the equation of the any physical quantity relate with the other physical quantity. Right? Okay. Now the speed of a transverse wave in a stretched string is depends on first the linear mass density of the string and tension in a string. Therefore we can write like this way: the speed of transverse wave in a stretched string depends on first linear mass density denoted by mu, or there is also known as mass per unit length of a string. Mass per unit length of a string. And second, this depends on tension of a string. Tension, capital T, of a string. Therefore, in a stretched string, the speed of a transverse wave depends on two factors. One is the linear mass density mu, and second is the tension of a string. Dimensional formula of linear mass density is mu is equal to mass upon length. Therefore, dimensional formula of mu is equal to m1 upon L1. So it's equal to m1 L minus 1 P0. And tension T is equal to dimensional formula of force. Dimension of force. We know that the dimension of a force is m1 L1 T minus 2. These are the dimensional formula of linear mass density and tension T of a string. Okay, now to generate speed V, that means the dimensional formula m0 L1 T minus 1. Combine combine mu and T in such a way that we obtain dimensional formula m0 L1 T minus 1. Our aim is to obtain the speed of a transverse wave in a string. Therefore, to generate the speed V, dimensional formula is m0 L1 T minus 1. Combine the two factors mu and T in such a way that the dimensional formula obtained is m0 L1 T minus 1. The dimensional formula of mu upon T is dimensional formula of mu is m1 L minus 1 T0 upon T. So m0 L1 T minus, that is the 2, T minus dimensional formula of tension is m1 L1 T minus 2. Right? Okay. Just make it. So we have to, the dimensional formula of this is T upon mu. Therefore, T upon mu, T, that's the dimensional formula is m1 L1 T minus 2. While the dimensional formula of mu is m1 L minus 1. m1 L minus 1 T0. Therefore, 1 times m1 m1 cancels. In denominator, L minus 1 comes into the numerator, becomes the positive. Therefore, L2 T minus 2. Therefore, m0 L2 T minus 2. Clear this thing? Okay. Therefore, if the speed v depends on mu and t, therefore, if speed v depends on mu and t, therefore, wave speed v is equal to c into under root of t upon mu. Here the c is proportional constant, or the dimensional less constant, and its value is unique. Dimensional less constant and its value is unique. Right? Therefore, the v is equal to under root of t upon mu. T upon. Therefore, the speed of a transverse wave depends on the linear mass density and tensor of the string. That is not depends the frequency of a wave. Thus, the speed of a transverse wave depends only on linear mass density, mu, and tension in a string. It not depends on frequency of a wave. So this way we can derive the equation of speed of a transverse wave in a straight string. Again, obtain the equation of the speed of transverse wave in a one-stage string. The speed of a transverse wave in a straight string depends on first the linear mass density or the mass per unit length of a string, and second tensor T of a string. First we have done the dimensional formula of both. The linear mass density is mass per length. Therefore, mu is equal to m1 upon L1. Therefore, m1 L minus 1. T is not present. Therefore, T is 0. And the tensor T has the same dimension of the force. Force has the dimensional formula m1 L1 T minus 2. To generate the speed v, dimensional formula of the speed is m0 L1 T minus 1. Combine the mu and t in such a way that we obtain the dimensional formula m0 L1 T minus 1. Now, as we take the ratio of these two quantities T upon mu, T is the m1 L1 T minus 2 divided by m1 L minus 1. The dimensional formula of ratio T upon mu is m0 L2 T minus 2. On the right hand side, that is the dimension of square of a speed. Therefore, if the speed v depends on mu and t, therefore the equation of the wave speed v is equal to under root of t upon mu. So here we introduce the constant, says the dimensionless constant, and its value is unit. Therefore, V is equal to under root of P upon mu. Thus, the speed of a transverse wave depends only on linear mass density mu and tension of a string. It is not depends on the frequency of a wave.